A laboratory in Hangzhou, China. A block the size of a human fist sits on top of a cherry blossom. The flower does not bend. This solid material weighs 0.16 milligrams per cubic centimeter, less than the air around it. Air weighs 1.2 milligrams per cubic centimeter. This material is 7 times lighter than the air you are breathing right now. It is lighter than helium, only twice as heavy as hydrogen gas. This is graphene aerogel, the least dense solid material ever made, created in 2013 by a team at Hangzhou University. The record still stands. Nobody has beaten it. Before we go further, where in the world are you watching this from? Back to a material that should not exist. There are 2 questions you need answered immediately. How they made something solid weigh less than nothing, and why, 13 years later, it is not cleaning up every oil spill on Earth. The first question has an answer. The second one is where it gets uncomfortable. Every solid material you have ever touched, steel, wood, plastic, glass, bone, is denser than the air around it. That is physics. Atoms take up space. The tighter you pack them, the heavier the material gets. Air at sea level weighs about 1.2 milligrams per cubic centimeter because its molecules are spread out, bouncing against each other in constant motion. A solid material has to weigh more than that because atoms in solids are locked in place, clustered densely together, unless you build a structure so full of holes that most of what you are holding is empty space. Graphene aerogel is 99.98% air. The other 0.02% is a scaffold made from sheets of carbon atoms, 1 atom thick, woven into a 3-dimensional web so delicate that if laid flat, it would cover several football fields. In its folded form, it fits in your palm and weighs almost nothing. Subscribe if you are new here. Professor Gao Chao from Zhejiang University's Department of Polymer Science and Engineering led this research, directing a team working in a state-of-the-art facility where precision was measured in billionths of a meter, a scale so small that individual atoms could be positioned and counted. His team was trying to solve how to clean up oil spills without adding weight to water. Traditional methods use absorbent booms and skimmers, slow, labor-intensive technologies that require boats to physically move through contaminated waters, and the materials become waterlogged and heavy as they soak up liquid, eventually sinking or requiring constant replacement, which can take weeks or months for a single large spill. Gao needed something that could soak up oil, repel water, stay light enough to float indefinitely, and be wrung out and reused without degradation. The only way to get all those properties was to build it at the atomic level. Graphene, a single layer of carbon atoms arranged in a honeycomb pattern, has more surface area per gram than any other known material. If turned into a sponge with the right structure, it could hold hundreds of times its own weight in liquid. But graphene alone is flat. Stacked sheets collapse into graphite, dense and useless for their purpose. Gao needed to hold the sheets apart in 3 dimensions, like an invisible framework keeping them suspended in space. The technique is freeze-drying with liquid nitrogen. You start with a solution of carbon nanotubes and graphene oxide mixed in water, creating a viscous liquid that Gao's team poured carefully into containers, watching for any disturbance that might wreck the alignment. The nanotubes act as spacers, tiny support beams holding the graphene sheets apart. You freeze it with liquid nitrogen in seconds. The liquid becomes solid almost instantly, a violent phase change that locks the structure in place in its perfect arrangement. Then you do not melt the ice. You remove it in a vacuum chamber until it sublimates, going directly from solid to vapor without ever becoming liquid again. If you let it melt, the structure collapses under its own weight as the scaffolding falls and crumbles. By freeze-drying, you remove the water and leave the scaffold standing intact, hovering in emptiness. The result is a 3-dimensional web of graphene and carbon nanotubes with nanometer-scale gaps, spaces so tiny that 100,000 could fit across a human hair. It is extraordinarily light because there is almost no mass, mostly empty space, like holding a cloud you can touch. It is elastic. The web compresses under pressure and springs back to its original shape when released, bouncing back reliably. It is hydrophobic, but oil can penetrate its structure. Oil molecules are larger and less polar than water, so they slip into the gaps and stick to the carbon surfaces through weak chemical attractions. Because it is conductive, electricity flows through the carbon web, and a small electric current heats it slightly to make oil flow out for reuse without damage, allowing it to be wrung out like a sponge. Gao's team tested it with motor oil, diesel, chloroform, and ethanol, absorbing between 215 and 900 times its own weight, depending on how thick or thin the liquid was. They published results in Nature in February 2013, the premier scientific journal read by researchers worldwide, which signaled to the scientific community and beyond that something extraordinary had been achieved. The material is temperature stable, performing identically at -196 degrees Celsius and room temperature, meaning it could operate in Arctic ice or desert heat. Oil spills are catastrophic because oil spreads fast, following currents and wind, covering vast areas in hours, moving faster than response teams can track, and existing cleanup methods are slow and expensive. Skimmers and booms contain only so much before they must be emptied and replaced, a process that can take days. Chemical dispersants spread contamination instead of removing it, breaking oil into smaller droplets that sink and contaminate the seafloor, poisoning bottom ecosystems for years. Burning works only in calm seas and creates air pollution, trading one environmental problem for another, choking the air while cleaning the water. In 2013, Gao's graphene aerogel offered something different. Drop it onto an oil slick, let it soak up the oil in minutes, pull it back out, squeeze it dry, and reuse it. No waste, no added chemicals. Because it floats, heavy equipment is not needed. No barges, no cranes, no ships designed specifically for cleanup work. It sounded like the end of oil spill cleanup, except that was 2013. We are now in 2025, and graphene aerogel is not cleaning up oil spills. It is sitting in laboratories. So what happened? 3 compounding factors. First, cost. Graphene is not cheap. The freeze-drying process works reliably in a laboratory, where every variable is controlled. Temperature, humidity, equipment calibration, technicians watching every step. But scaling to industrial volumes requires infrastructure that does not yet exist. Multiple freeze dryers running continuously 24 hours a day, purification systems to produce graphene oxide at scale, vacuum chambers large enough to process tons per day instead of grams. Estimates for similar materials run into tens of thousands of dollars per kilogram. Oil cleanup budgets are big, but cheaper options work reasonably well. Not perfectly, but adequately. And adequacy is good enough when the alternative is expensive. Second, durability. Open ocean is not a laboratory. Waves, wind, salt water, UV exposure from sunlight degrade materials over time, wearing away their strength. Graphene aerogel is fragile. If pieces break apart in water, you cannot recover them. Fragments are too small and too light to collect with nets or screens. They float away, adding contamination instead of removing it, which defeats the purpose entirely. Third, logistics. Oil spills happen hundreds of miles from shore. Response times are measured in hours. The first few hours are critical because oil spreads exponentially, doubling in area almost hourly. You need stockpiles ready to deploy immediately and ships or aircraft to carry it fast. Graphene aerogel is light but bulky. A cubic meter weighs almost nothing, but takes up a cubic meter of space on a vessel, crowding out other equipment. Recovery becomes another problem if it breaks apart in rough seas or mixes with debris. The science works. The material does what it is supposed to do in controlled conditions. Getting it from a laboratory bench to a cleanup vessel in the middle of the ocean is a gap that has not been bridged. Not because it is impossible, but because nobody has committed the resources to make it happen. And committing resources requires someone to believe the payoff is worth the risk. But graphene aerogel is not the only ultralight material stuck in limbo. In 2011, HRL Laboratories in California made a nickel-based aerogel at 0.9 milligrams per cubic centimeter that could sit on a dandelion without crushing the seeds. Designed for aerospace applications where weight is the enemy and every gram saved improves performance. still in the lab. In 2015, Lawrence Livermore National Laboratory created a carbon nanotube aerogel under 1 milligram per cubic centimeter for battery electrodes and supercapacitors, where weight and conductivity both matter for devices that need to store energy efficiently. Still in the lab, in 2018, a Swedish team made biodegradable nanocellulose aerogel that insulated better than foam while being fully compostable, solving environmental concerns that plague traditional foam insulation. Still in the lab, the pattern repeats. Extraordinary properties documented in peer-reviewed journals, publication, press coverage with optimistic headlines, breakthrough declarations by universities announcing they have solved problems, then disappearance from public view. Not because the materials do not work, but because the gap between working and being economically viable at scale is enormous. A chasm measured in millions of dollars and years of development, and most research teams lack the funding or infrastructure to cross it. Gaochao's team continued after 2013, driven by curiosity and institutional support that allowed them to pursue fundamental questions without immediate commercial pressure. In 2016, they showed graphene aerogel could support chemical reactions, acting as a catalyst scaffold with enormous surface area where molecules could interact efficiently. In 2019, they demonstrated it could absorb low-frequency noise that traditional insulation struggles with, working through an entirely different physical mechanism where the structure vibrates and dissipates energy. In 2021, they showed adding boron nitride nanotubes made it more heat-resistant without increasing weight, improving stability at high temperatures above what graphene alone could achieve. But none moved the material to production, because research funding and commercialization funding are different animals with different goals. University labs prove materials work, that is their purpose and their strength. They cannot build factories, cannot run assembly lines, cannot manage supply chains that span continents. That requires private investment and clear profit paths. Right now, economics do not add up. Graphene production costs too much per unit for markets to absorb at scale. Freeze drying is too slow and energy intensive to achieve high throughput, processing only kilograms when industries need tons. The market for ultra-light absorbent materials is not big enough to justify the capital expense. Not yet. But that could change. Graphene production is getting cheaper as competition increases and techniques improve. Chemical vapor deposition was once the only option, a slow and expensive process that could make only tiny quantities. Now, mechanical exfoliation and liquid phase processing produce graphene at fractions of the cost, each breakthrough reducing prices further. Companies in China, South Korea, and the United States are scaling production for batteries, composites, and coatings. They are investing because they see long-term demand growing. As volume increases, price drops, following the predictable curve of manufacturing economics. Demand for lightweight materials is growing across industries. Aerospace faces pressure to reduce fuel consumption. Every kilogram saved translates to thousands in fuel savings over a plane's lifetime, making airlines eager to adopt lighter materials. Electric vehicles need lighter structural materials for battery weight management, since a lighter vehicle uses less energy per mile and travels further on a charge. Wind turbine blades, drones, satellites all benefit from weight reduction, from efficiency gains to extended operating life. Environmental pressure is mounting from governments and voters concerned about climate and pollution. If graphene aerogel becomes cheap enough and deployable, governments and environmental agencies will pay for it. The question is not whether it will happen, the question is when. Hangzhou OLED Works announced in late 2023 they were developing commercial production for graphene aerogel, targeting water purification and oil spill response at under $5,000 per kilogram. Still expensive by most standards, but approaching plausibility for critical applications. Aerogel Technologies is experimenting with graphene formulations for aerospace insulation and battery thermal management, working with equipment manufacturers to design production systems that could eventually scale. In 2024, KAIST published research on a microwave-assisted freeze-drying technique that cuts processing time in half, lowering costs, and moving the material closer to economic viability by making production faster and cheaper. The deployment problem remains. getting this material to disaster sites without damage or contamination, without fragmentation as pieces break apart, without it degrading in salt water or UV light after a few days at sea. Pre-deployment stockpiles at ports and offshore platforms could work, but require companies to commit financial resources before prices become competitive and demand is proven. Integrating aerogel into existing cleanup equipment like booms and skimmers offers another path, requiring collaboration between material scientists working in universities and equipment manufacturers who understand field operations, logistics, and what can actually survive in the ocean. China dominates graphene production, producing over 50% of global supply and holding more patents than any other country, by a significant margin that has only widened. They control most graphite supply chains, the raw material from which graphene is extracted, giving them leverage throughout the industry. The US Department of Energy and European Union are funding research to reduce dependence on Chinese supply, but remain behind in both production capacity and patent development. Hangzhou's 2013 breakthrough signaled China's commitment to long-term materials research, the kind of investment that pays off over decades without immediate returns. Materials breakthroughs follow consistent patterns. Laboratory discovery where something new is created. Incremental improvements where researchers refine it. Cost reductions where production gets cheaper. Then widespread adoption across industries. Lithium-ion batteries invented in the 1970s became viable in the 1990s and dominated energy storage by the 2010s, transforming portable electronics. Solar panels demonstrated in 1954 reached cost parity with fossil fuels in the 2010s, transforming global energy infrastructure. Graphene, isolated in 2004, is following a similar curve, though accelerated by the pace of modern research and investment. Graphene aerogel is in the middle of this progression. Discovery complete, improvements ongoing, costs dropping steadily, applications tested in laboratories, infrastructure being planned by companies watching the technology mature. Hangzhou's 2013 record of 0.16 milligrams per cubic centimeter faces competition from other research groups worldwide. University of Central Florida achieved 0.18 in 2021 using plasma etching to create the structure more efficiently. Japan announced 0.17 milligrams per cubic centimeter in 2023 using supercritical carbon dioxide drying instead of liquid nitrogen, achieving similar lightness through a different method. While Gau's record still stands, the shrinking gap indicates more researchers attacking the problem from different angles, driving innovation, cost reductions, and accelerating the laboratory-to-market timeline. Graphene aerogel's significance lies not in lightness alone, but in combining extreme lightness with functionality, holding weight without collapsing, conducting electricity for heating or sensing applications, absorbing liquids selectively based on their properties, and recovering from compression without permanent deformation. This combination enables solutions previously impossible, spacecraft components weighing almost nothing that reduce launch cost, efficient insulation for extreme environments from space to deep sea, cleanup materials that float indefinitely without saturation, and energy storage, where the scaffold itself weighs less than the energy held inside. Engineering challenges remain solvable now that the material exists and its properties are understood. People do not trust things that feel impossible. When you hold a material that weighs less than air, your brain does not process it correctly. It defies intuition built over a lifetime of experience with objects and gravity. It feels fake. It feels like a trick. That distrust translates into hesitation, to invest, to adopt, to deploy at scale. The aerospace industry is conservative by design because failures are catastrophic and costly, measured in hundreds of millions in lost vehicles and lives. The environmental cleanup industry is underfunded and risk-averse, bound by existing procedures that work acceptably. The energy storage industry is locked into lithium-ion because the supply chain is already built and the economics are predictable. Breaking into any of those markets requires more than just a better material. It requires real-world proof, a cleanup operation where graphene aerogel outperformed everything else, visible and measurable, a satellite launch where weight savings made the mission possible, a battery prototype that lasted twice as long, something concrete, something undeniable. That success story might already be in the works. In early 2024, the Chinese government announced a pilot program to test graphene aerogel for oil spill response in the Bohai Sea, one of the world's busiest shipping corridors. They deployed 500 kilograms across 3 test sites in the heavily trafficked shipping lanes. Early reports suggest it performed better than conventional absorbents in calm conditions, absorbing oil faster and more completely, removing oil in minutes instead of hours. Though it fragmented in rough seas when waves broke pieces apart, preliminary results were encouraging. If they solve the fragmentation problem, perhaps with a protective mesh coating or a binding agent that holds pieces together, the material becomes viable for real-world use. Once viable in one application, the others follow. Aerospace sees it working in the ocean and asks, what if we use it in insulation? Energy storage asks, what if we use it in batteries? Each success opens the next door. A material that weighs less than air exists. It works. It has been tested. The applications are real and documented, but the gap between laboratory and deployment is still open. Cost is too high for current markets. Infrastructure is not built. Trust is not there. Yet all of those are solvable problems, each with a solution. Cost comes down with scale. Infrastructure gets built when demand justifies it. Trust comes from success stories. The question is not whether graphene aerogel will matter. The question is when. That depends on who is willing to invest in production before orders are guaranteed. Who is willing to deploy before validation? Who is willing to bet that the impossible thing is not a laboratory curiosity, but the foundation of an industry that does not exist yet? What makes this story important is what it represents, a fundamental shift in where breakthrough research happens. For decades, advanced materials came from the West: Silicon Valley, Cambridge, Berlin, MIT. China was the factory producing what others designed. That arrangement stopped working when China decided it no longer needed to wait for someone else to invent the future. China now leads in high-temperature superconductors, quantum communication, fusion reactor design, and synthetic biology. They are not copying anymore. They are originating. Western countries that assumed they would always hold the technological edge are scrambling to catch up. This is not about one material. It is about a pattern. And the pattern is accelerating. The pattern extends beyond materials. It is visible in infrastructure. China built more high-speed rail in the last decade than the rest of the world combined. In energy, they installed more solar capacity in 2023 than the United States has installed in its entire history. In batteries, electric vehicles, semiconductors, every industry has the same story. A decade ago, Western companies led. Today, Chinese companies lead, or are on the verge of leading. Western research labs are constrained by funding cycles and risk aversion, limited to projects that promise returns within 5 to 10 years. Chinese institutions are encouraged to pursue long-term, high-risk projects, funded by national strategy, not quarterly earnings reports. That difference in incentive structure produces a difference in outcomes. A block of graphene aerogel sitting on a cherry blossom, lighter than air, was not a trick. It was a signal. It said that the rules everyone thought were fixed, that breakthroughs happen in Silicon Valley or Cambridge or Berlin, those rules are no longer true. The future is being written in laboratories you have probably never heard of, by researchers whose names do not appear in Western press. And it is being written faster than anyone expected. When graphene aerogel matters, the question will not be who invented it. The question will be who built the infrastructure to deploy it, who took the risk to scale it, and who understood early enough that the material itself was never the point. The point was the system that produced it. That is the real breakthrough, and that is what you need to be paying attention to. Subscribe and turn on notifications. The next story makes this one look small,